And for today, our speaker for today inauguration today function is Dr. Pryadarshi Chinmoy Kumar. Sir is presently working as a scientist as WIHE Dehradun, India. First of all, sir, I would like to welcome you on the behalf of NIT Raipur family. Thank you for your precious time.
Thank you.
Sir has completed his BSc in physics from College of Basic Science and Humanities out, Bhubaneswar, MSc Geophysics from the Department of Geophysics, Andhra Pradesh University, Vizag, and PhD from ACSIR National Geophysical Research Institute, Hyderabad. Sir has authored a book named Meta Attributes and Artificial Networking, a new tool in seismic interpretation. Sir has also volunteered as a reviewer in many respected journals like elsewhere. He has been awarded with ONGC Meritorious Fellowship, DST Inspire Fellowship, Dr. G. Negi Young Scientist Award, and many more in his buckets. So, sir, thank you once again, and I hand over this session to you.
Uh, yeah, thank you, Priyanka, for your nice introduction. It's my privilege. Let me uh, share how to share. Uh, into- are you able to see my presentation?
Yes, sir. So, can you please make it in a slide mode?
Okay, I have made it in slide mode. Now it is visible.
Yes.
Okay. Thank you, Priyanka, for your nice introduction, and thank you, Mriduji and Dr. Sagar Mishra and many more faculties out there for inviting me to share my views, my research thoughts in front of young students and research scholars. I'm very much obliged near you, in today's presentation, I will make it sure that not to bore you, because I think it's evening hour, so you must be in exciting mood, rather not to be bored. So most of my presentation will be in a storytelling format, showing you some interesting images and saying much about geological approaches and if you want to more know more, detail regarding the algorithms or the process, the mechanism hidden behind these works, then you can follow my papers and you can follow my recently published book, which is published internationally worldwide. So with this, I start my today's talk, and I'm going to present before you all on a topic entitled as AI approaches for interpreting subsurface images and structures. When I say interpreting subsurface images, it means that when I try to look into the subsurface below the surface where I'm standing, if I try to scan the environment below, scan the environment on the top on which I am standing. If I want to scan the environment below it, then that means that I am trying to do some type of some type of image or some type of interpretation to the environment that is present in the subsurface. So that means that interpreting subsurface and images and what type of geological structures are there. When I try to scan them, then I try to get an imprint of those structures. Then what are those structures? When I see an image, then what are those structures? How can I interpret it using advanced technique, which is known as artificial intelligence? And this artificial intelligence nowadays has been so popular and is being used in each and every sector of human activities as well as industrial processes. This technique has now been a hot topic, or the humor of the day. So the contents of my talk here are as follows. So before I take you into before I make you a journey through the artificial intelligence, I would like to introduce that where I am located and what research I do, so that you can get at least a glimpse that the instructor, I mean, what research I do, and how I try to get motivated to join this artificial intelligence as one of my research expertise. Then I will also introduce you to a group that we have in Wadia Institute of Himalayan Geology. So you youngsters could be motivated, and if you can and if you can think that to continue your future research, you are always welcome to join this group. Then I will take you into a journey of artificial intelligence, directing you that why we need artificial intelligence and what is the essence of artificial intelligence. Then the historical evolution of neural networks, an overview of neural learning and networks, and then why AI for subsurface interpretation? Like as per the today's talk that going to deliver, I'm delivering the talk on subsurface interpretation. You must be thinking that why AI? Can't we do it in a general process, or can we apply the fundamental techniques that we read in our textbooks, or that is the techniques that is existing? Can't we apply those techniques for interpreting subsurface? So why do we need to learn AI, and do we need to appreciate this technique? After that, I will show you about 10 to 11 case studies that we have performed not only in Indian sedimentary basins, but also worldwide sedimentary basins. And finally, I will conclude my talk. And I will also illuminate you with our sponsors and collaborations that we have been building since last couple of years for carrying out this exciting piece of work. Yeah. I am here at Wadia Institute of Himalayan Geology, which is located in the city of Dehradun in the state of Uttarakhand. And as you all know, that the Dehradun is the capital city of Uttarakhand and is a very nice place to visit. It has a very exciting time, especially during the winter. You enjoy the snowfalls, you enjoy the hilly terrains, and especially this valley, this Dehradun is especially hydrologically it is known as a Doon Valley, and it lies within the watersheds of Ganga and Yamuna rivers. The city is famous for the beautiful landscape it has, and the climatic condition is very smoothing. In summer, neither you will have neither you will be worried for the huge heat, and in the winter also you will enjoy the heavy I mean cold that you will feel at Dehradun. And within the Dehradun, there is an institute where I work that is called as Wadia Institute of Himalayan Geology, which is an autonomous institute of Department of Science and Technology, a government of India. Initially, the institute was known as Institute of Himalayan Geology, and it got established way back June 1968 at Delhi University, and later on got shifted to Dehradun during April 1976. The institute was later named as Wadia Institute of Himalayan Geology in the memory of its founder, late Professor D.N. Wadia. And my research interest, as you can look here, my research interest lies within exploration geophysics, geological and geophysical interpretation, structural and stratigraphic interpretation, seismic geomorphology, 3D seismic and attribute workflows, machine learning and its application, sedimentary basin studies. So here is the fourth part of my research, which deals with machine learning and its application. You can find me in Google Scholar. You can download all of my papers there. Also, you can find me at ResearchGate, and you can read my comments, my articles, and also you can follow me at ResearchGate. Within Wadia Institute of Himalayan Geology, there is a newly established laboratory which started in the year 2020, just recently started, and the name of the laboratory is SIL, which is known as Seismic Interpretation Laboratory. Basically, the aim of this laboratory is to interpret high-resolution seismic data to understand the subsurface tectonics and geological processes of northeastern Himalayas, and the northwestern Himalaya, as well as the central Himalayan regions. We all are thankful to Dr. Kalachan Sen, the director of Wadia Institute of Himalayan Geology, under whose guidance this laboratory came into its existence. Now, what research we do at this place? The research at SEAL primarily deals with the four different parts, in which the first part deals with basin tectonics and its evolution, subsurface structural and stratigraphic studies, subsurface geomorphologic studies. Then the last theme is on technique, design, and development. And we basically, the entire research approach falls within two domains. One is the fundamental approaches of seismic data interpretation, and the second process is advanced techniques that uses machine learning to interpret subsurface features and tectonics. And this is the laboratory that we have. We have a small group of students working with us. Few postdoctoral students. We have few postdoctoral students. We have doctoral students, and we have out of those doctoral students, many of them are CSI and NET qualified. Some are GST Inspire qualified, and we have one SPM fellow, Prasad Mukherjee fellow in our laboratory. And all these people are from different domains. Some of them are from geology, some of them are from geophysics, and even if now we also got some applicants, we have received applications from physics domain. So we have, we have a very interdisciplinary range of students, where we try to share each of our thoughts, and we try to research on these four themes, focusing on this gigantic Himalaya and its adjoining regions. Now, so artificial intelligence, why and what? Artificial intelligence, as you all know, is a branch of computer science. It's my humble appreciation, and I'm always obliged towards this computer science branch, because of which we people are able to learn your techniques, and we people are able to learn the way you try to formulate certain problems. So that becomes very helpful to geophysicists and geologists. So artificial intelligence is a branch of computer science which is mainly concerned with building, smart machines capable of performing tasks that typically require human intelligence. And you must have and you must have heard about all these things like Siri, Alexa, development of several smart assistants and self-driving cars, robo advisors, conversational bots, email spam filters, Netflix recommendations. So all these things are guided by what we call as artificial intelligence. They have been designed with the aim of artificially how a machine can artificially work by getting a command from the master. Why should we learn about artificial intelligence, and what motivates us to learn about artificial intelligence? Now, you just imagine that you are standing in a group of gathering in a very highly gathered place, where there are very youngsters, there are some girls, boys, some old ladies, and some old people. Now, in this gathering, if you try to ask the question to certain person, like for example, if you pick somebody and you ask that, how do you look like? Are you fair enough, or are you black? What is your complexion? Then immediately you say, yeah, this gentleman looks a bit, he's very fair. He has long and curly hairs. He has a beard in his face. He wears spec. So this is the particular gentleman that I am looking for. It's become easy to answer all these questions for you. But Now you imagine you are going to a supermarket, and in supermarket there are several grocery items that you are going to purchase. When you're purchasing the grocery items, after you have completed your purchase, you try to calculate that how much does each of these item cost, what is the discount that I'm getting, how much rebate, and how much amount that I'm going to pay. So when you try to perform all these calculations, obviously you get frustrated. It is because human brain is so designed that if you want to do some qualitative analysis, human brain does it in a very faster way, or human brain is qualitatively fantastic. But when you try to do some quantitative approaches, or when you try to compute something, when you try to calculate something, you get frustrated, or you get exhausted. So what exactly is happening? You see, the thing is that human brain is very attracted to certain things, but when the computation part comes, human brain fails. So why? So the question is that if can we amalgamate, or can combine this qualitative and this quantitative approach by using certain algorithms, or if we have a certain set of a system that can control all these parameters, and that can immediately give the answer by listening to the human brain, or by listening whatever the master speaks. Won't it be very fantastic? Yes, that is the motivation of building artificial intelligence, or AI, which is an amalgamation of human intelligence and the machine intelligence. The machine that is getting trained under the guidance of human brain, then the outcome which comes, it comes in a very automated way, or what we call today in everywhere, in every discipline, that is called as artificial intelligence. So this is the motivation of using artificial intelligence to automatizing a given problem, and to find out its solution at a very easier way. If we go back to the historical evolution of this artificial intelligence, way back to 1950s or 40s, I would like to always quote these persons, Mukuluk and Pitts, from which these networks started to develop. And during the 40s to 80s, uh, um, techniques started to develop. People used to use several type of networks that could try to mimic, or try to understand that what the human behavior is, and how does human approaches could be mimicked using certain mathematical processes, or using certain mathematical equations. Then from 1980s towards 2010, came into picture what we call as machine learning. What is machine learning? Now, suppose if you have some equations given to us, if we have some mathematical equations given to us, now how can a machine try to understand this mathematical equation and use certain inputs and give the output? That the machine will try to learn what the master, what the user wants to give that. So this process got started, got evolved during 80s to 2010. Then from 2000, 2000 onwards, 2010 onwards, this learning process got divided into, basically into what I believe, it got divided into two different approaches. That is shallow level neural learning and deep level machine learning, where the difference is nothing but the arrangement of the arrangement of several networks, or several processes, in which, computationally the system gets more complicated. Computationally the system performs huge amount of computation to capture large amount of data, and give it and give the output in a very much easier way. So in this way, in the if you feel the, if you see in the field of seismic, then in the field of seismic, there was a breakthrough, not only in the field of using the network, but also designing of the network. After, I think, after 1950s, there was a breakthrough where the theory of perceptron started to be, I mean, very famous within this design of several machine learning algorithms. And till date, you might be reading several books and several literatures. Several newer algorithms have been popularized, and several newer algorithms have been designed based on the what the user needs. So in this way, the artificial intelligence evolved from late 40s till date. The entire this algorithm, always remember, these algorithms that are being developed, or that are coming into the market, or the algorithms that you are getting interested to work, is based always on certain problem that the user, what is the problem that the user thinks. It is not that there are several algorithms, and the user is mandated to use several algorithms. You should have a problem that this particular problem could be addressed using certain algorithm. Then based on that algorithm, you try to perform your AI stuff or your AI related work. But we all must appreciate always the historical evolution, how it has evolved over time, and how this evolution motivates us to pick up a problem and use this technique to address to solve that particular problem in a very or to solve that particular problem with keeping an aim in automatizing the process. Now, how this the concept of this network came into existence? What was the inspiration behind it? The inspiration behind it was scientists or researchers got interested by looking into what is called as biological neuron. I'm sorry. What is called as biological neuron, because this biological neuron, if you see inside the human brain, structurally the neuron consists of three major parts. One is called as dendrite. These are these are the dendrites, the soma, and the axon. What happens? The signal gets entered through these dendrites. Again, it gets processed inside the nucleus, and once it gets processed inside the nucleus, through the axon, it gets transferred to the next to the next neuron, and in this way, these neurons are thousands of neurons are interconnected with each other, which tries to do the job in a very in very in a fraction of second, and within the human brain, that there are billions of networks of these neurons through which the signal gets transmitted in a very quicker way. So, being inspired through this system that is present in the human brain, scientists try to design uh, what a neuron artificially. That is called as, why we call it as artificial. Artificial means you're trying to design it yourself. So scientists try to, being motivated by this biological system, they try to design the set of neurons, what we call it as mathematical neuron. What does it mean? It means that a particular set of architecture which contains some mathematical equations, and which can crystally elaborate that how the input enters into the system, and what happens within the system, and how the input and how from the input to through the processing the outputs gets generated. So this type of architecture was called as the mathematical neuron. As you can see here, we have certain inputs, and the inputs goes into an association layer where the inputs are summed up. Now see, in biological neuron, what we have read certain dendrites. There are certain dendrites. Through these dendrites, the signal tries to enter. The signal tries to gets processed within this nucleus. Similar process is being mimicked while designing the mathematical neuron. Like there are certain inputs. This inputs gets into another layer where all the inputs are collected. Then the inputs are mathematically processed, and once the inputs are mathematically processed, they are rescaled, and once they're rescaled, you get a particular output that what you are trying to expect, or what you are trying to predict. So in this way, you see how beautiful is the science, how researcher try to understand how mathematicians, how physicists try to understand that let us try to mimic that what nature has given to us. Let us try to make a replica or try to reconstruct in such a way that those things could be used in a day-to-day life, or in our day-to-day works. This is the beautiness of the science, or this is the beautiness of the way, I must say, you all researchers should think of. Now, in the process, now the question is how the machine will try to learn. If you try, you definitely now assume that a mathematical equation is viewed through this system, or through this using this mathematical neuron. Now let us consider that a mathematical equation is generated, but the machine, as you all know, the machine, for making it understand the mathematical equation, you need to train, you need to make it learn. So when scientists now thought that how the machine could be learned, so from there started the process what is called as neural learning. Neural learning is categorically divided basically into three different sectors, where you have where you call as a supervised set of learning, and you call that is an unsupervised set of learning, or you call it as a reinforcement of learning. A supervised learning is a process in which you try to train the network, or try to train the machine using some examples, like how to make it clearly understandable in a layman language. Assume that uh, you have a small you have a kid with you. Now you say the kid that look, I'm giving you a box. Now the box contains red balls, the box contains blue balls, the box contains white balls. Now you have to separate the balls and give it to me. Now the child will ask you that how can I do it? You must make me understand that what is the blue ball? How will I recognize the ball as a blue? How will I recognize the ball as a red? Or how will I recognize the ball as a white? At that position, what you say, that if the color, or if the ball looks like this, or if the ball is having such type of color, then that is called as a blue ball. If a ball has certain type of color, then that is called as a red ball. If a ball has certain type of color, then that is called as a white ball. So based on this, you now said the child that you gave some examples, that these are the examples in which you understand that that is the process by which you separate the amount of balls that is present within the box into blue, white, and blue, red, and white. So following your instructions, the child then starts to segregate it into three different categories. That is called as red ball, that is called as blue ball, and that is called as white ball. So this type of learning scheme is called as a supervised learning scheme, where you give some examples, and from those examples, the machine tries to establish a nonlinear relationship between the input and the target variables. Now, a second system of learning, which is called as the unsupervised learning. Now, unsupervised learning, how to understand this unsupervised learning? Now, suppose you think that there are certain balls in the pocket, and some balls are not. I mean, they are clustered. You don't give the child any type of examples. So, based on the ability of the child, the child now tries to categorize these balls into certain properties or certain colors. So in that process, where you don't have any examples available with you, but in this process, the child himself tries to learn and tries to generate an output. So such a process, a learning process where no a priori information is provided to the system, and the system has its own ability to analyze and determine some common features which is present in the input. That type of learning is called as unsupervised learning. Again, in a part of supervised learning is called as a reinforcement learning, where only supplied information is the answer indicating as to whether the computed output is correct or incorrect. From the supplied information, there'll be answer. Already the answer will be present within the supplied information, that the output what is going to come, is it correct or not. And if the child gives a correct answer to it, then a reward will be given. And if the child is not able to recognize that correct answer, then the penalty will be given to the wrong answer. So in this way, three different categories of learning have been categorized. Now, how to use these type of learning? I would like to stress this point again, that a particular problem, always try to identify the problem, that what you are going to do. Are you going to are you going to classify certain things, that this is my yes, and these examples are my yes, and these examples are my no? Are you going to do certain type of like these practices, or are you going to understand the pattern which is present within the given problem? So based on the problem, you try to select that which type of learning mechanism you are going to use. Are you going to supervise? Are you going to use a supervised learning scheme, or are you going to use an unsupervised learning scheme? I must suggest that never go in a blind way, that you have given certain input, and you expect the machine that is using certain type of networks that will be giving you output. Like for example, if you go to the MATLAB toolbox, there is a toolbox present here, and you give certain input, it generates certain output, but at the end of the day, you don't understand that what exactly the machine is doing, and what exactly the problem that you are thinking. You must be thinking some unsupervised problem, but what the machine is doing some supervised problem. So based on this, you before making your network to run, or before making your network to give the answer to your problem, you must be pretty sure that what type of learning problem or learning mechanism that you are going to adopt, such that your nonlinear problem could be solved, or your complex problem that you are going to address could be solved at a much each. Now, there are plethora of networks that have evolved over time, as you can see here, like radial basis function, probabilistic neural network, then modular neural network, then self-organizing maps, several other networks like Hoppy field networks, learning vector quantizer, uniform vector quantizer, support vector machines. There are several type of networks available in the market, and several type of networks are available in several different. I mean, you can find the codes available in GitHubs. You can find now suppose recent versions of several MATLAB toolbox have all these networks available with you, and you can easily understand, and if you have certain problem, you can easily use a particular network to address that type of problem. Out of these, what I feel and what my research till date I have carried out, and my colleagues have carried out, my colleagues, we all have carried out our research using all these type of networks. But what I feel is very interesting to me is the classical MLP network, which is called as multi-layer perceptron network. And I'm a very strong supporter of this network. This was invented by Webos 1974, and later it was reworked by Parker in 1985. And slowly the network got simplified by McFarland et al. 1986, Sukhan 1988, and Rumelhut et al. 1995. I think after Rumelhut et al. 1995, the network has been more modified, and nowadays we are if we have one hidden layer, we can introduce n numbers of hidden layers within it, and we can make the network to be more complicated. And when the networks become more complicated, the more operations it tries to learn, it tries to perform. So basically, this MLP network, it has got three different layers: the input layer, and the hidden layer and the output layer. Into the input layer contains several inputs which are planned to be fed into it. The hidden layer, where all the neurons that are accountable for accumulating, processing, and modifying the incoming signals. And the output layer contains a fixed number of outputs. Again, see here you can have here the outputs, like for example I have shown here as two outputs. You can have the outputs as three. You can have the outputs as four. That is what I'm saying. Before using a network, you should have a clear understanding that what input you are giving and what output you are expecting. So based on that, you should design a network rather closing your eyes and just clicking on the button, going step by going from the input to output. As a result, what happens if you do like this? What happens? You will never be able to appreciate the beautiness of this neural network. So I always urge to all students, all researchers, that we should have always a clear understanding that what exactly the problem is and what exactly we are trying to expect the output. So based on that, we can design the network that we have with us. Going more into recent scenario, now the industry has moved into rather not shallow. It has not been restricted to shallow neural network. Rather, people have now researchers have now moved into a set of other networks where we call it as a process of deep learning, where nowadays you must be having known about convolutional neural network, where you have certain processes called as downscaling an image and then upscaling an image and generating its output. Now, let us come into reflection seismic. As you, I think if many of you understand seismic, what is reflection seismic, I just give you a hint. Reflection seismic is a type of geological technique, geophysical technique, where we try to generate waves, and it tries to enter into the subsurface, and it tries to give us the output. Uh, Putting it in other way, if you go to and if you go to a medical shop and you ask that to scan your body, to the doctor says that okay, you go and do the x-ray. What happens? You stand in front of the x-ray, and a rays tries to enter into, penetrate into your body, and finally you get an output in a form of a thin film. Now when you try to analyze it, what happens? Your body has been scanned by using certain type of rays, and from that you get the internal architecture of your body. So exactly that happens in what we call as a seismic. We have the source, we have some energy sources present in the surface. Then these energy sources, the seismic waves tries to propagate into the subsurface, and where you have and once at the point where there is a contrast in change in velocity and density, then the waves tries to reflect back into the surface, and in the surface we have several recording instruments, and those recording instruments capture the information, those from the waves, and finally these reflections are processed, and finally you get certain certain images like as I have shown you. So from here we try to understand that now this is the image that we have. Now based on geology, we try to understand that how the subsurface looks like, what are these type of signatures, and what are these type of signatures, what are these type of signatures. So this process of interpreting or understanding the reflection seismic is called as interpreting the seismic data, or seismic interpreting the data that has been obtained from using reflection seismic technique. Now, what do we interpret? For example, we interpret certain properties. Now, for example, let us consider that a person is standing at the middle of the road. Now, uh, You have seen that person. Now you came back to my room. Then I said that, did you meet Mr. Bain? You said that, oh, I'm sorry, I didn't, but yes, I think he is Mr. Bain. And I asked you that, how did you know that he is Mr. Bain? You said that, uh, Mr. Bain has long hairs, but those hairs are curly. He is wearing a spectacle. He is having a stick in his hand. He is wearing a coat, a black color coat, and his shoes are black in color and polished. So I think he is Mr. Bain. Then I said, oh, certainly you are correct. Now, do you understand how what is happening here? Now, the person, Mr. Bain, is being characterized within certain properties. What are those properties? Those properties are, he is having a black hair, a long black hair, which is curly in nature. He is wearing spectacles. He's having a black coat with him. He's wearing a stick which is standing upright, and his shoes are well polished. So all these are called as properties that is characterizing, or that is describing Mr. Bain. So what interpreters, those who use reflection seismic do, they try to understand certain properties of the subsurface, and based on that properties or based on that characteristics, they try to correlate with the geology and they try to infer the geology. Like for example, if I saw here you this, you say that, oh, this is a cube-like structure looking, but what are these? I say that these are nothing but a color representation of change in velocity and density. So taking these into account, velocity and density, and these characteristics of the wave, you try to generate certain properties. Like for example, you see this gray color image where you have like this type of linear features, linear features. So these properties are computed from this from the original data, that is simply a difference between the velocity and density. So as a geologist or as an interpreter, you try to understand these properties and you try to understand it in terms of geology. So these properties are nothing but called as attributes. Like for example, what are the attributes that characterize Mr. Bain? The attributes that characterize Mr. Bain are black curly hair, a black jacket, a long stick, the shoes that has been very nicely polished. So these are the properties that is characterizing Mr. Bain. So similarly, the properties that is characterizing this particular problem, it is called as attribute. And in seismic, these attributes have been significantly used over the past few decades for inferring subsurface properties and geologic features from reflection seismic data. Their analysis illuminated geologic features, revealed structural architecture, and also helped in quantifying specific physical properties. Like for example, but here I saw you is a change in, you see, this is a cross section of the subsurface. Now you see certain features giving a bouncer features. Okay. Now here what I showed you is only the amplitude change, or the change in the property, that is called as the velocity and density. Now using this change in the properties, I try to compute certain signature. Like for example, I try to compute what is called as reflection strength. Like for example, here I show you a volcanic top buried uh, deep below the subsurface in a marine environment. Now from this, I try to interpret certain properties. Now from these properties, I try to correlate with the geology and try to decipher the entire geological environment that must be prevailing in the subsurface. So this process is called as interpreting the seismic data using available certain geological stuffs and using these attribute properties. Like for example, As you can see, the bedding patterns of the subsurface, how these uh, how these reflection events or how this data have been are bending. Now from this, I try to extract certain properties, like for example, I try to extract frequency, I try to extract what is the phase of the data, I try to extract what is amplitude of the data. So based on these properties, I try to interpret the geology. So in this process, I try to interpret using seismic. My main aim is to interpret the subsurface geology. Now, where does AI comes into picture? Yes. Now the AI will come into picture. Now you see this image, particular image. Okay. Now this is the data. Rather, I will now not call it an image. I will say that you see this is map view of the subsurface. Now from this map view of the subsurface, I try to extract certain properties, and I got certain features like this. I got certain features like this. I got certain discontinuous features like this, which are not continuous, rather moving parallel to each other. And I got certain feature like meandering feature like this. My interest, I when I looked into this meandering feature, I get very annoyed at it. I said that, oh my God, I want to get revealed out of it. Because when I'm trying to compute a property called a similarity, where I have a similarity between traces and non-similarity between traces, when I have similarity between traces, then I say it as 1, and when I have non-similarity between traces, I call it as 0. And based on this property, I try to interpret the geology based on the similarity property. I try to interpret the geology that all these features that are running parallel to each other, these are minute. These are fault-like structures, and these are also some curved features. These are some curved structures present here. But what is this meandering structure present doing within this curved or these linear features? I'm getting annoyed, and I'm not interested for this type of feature. So what I said that I'm not interested for this type of features. Now the question is, can we use AI to get rid out of this? Now see what happened. Now how did I formulate the problem? I said that I am interested of these features, and I'm not interested of these features. That means what I'm doing, I'm trying to classify, I'm trying to categorize my this particular property based into two different domains. That is a feature of interest and feature of non-interest. So in this process, I try to generate a problem. So what type of problem I'm doing here? I try to generate a type of classification problem where I will try to feed the machine, and I will try to generate an output that is a classified output where I will be only interested for feature yes, and I may not be interested for feature no. So what happens? So in this process, when interpreters tries to interpret these type of features from the subsurface, for an young interpreter and for an experienced interpreter, always there is a trade-off between the observations. A noise to a young interpreter, a noise may an anomaly may be a noise to a young interpreter, but for an experienced interpreter, it might be a signal. That is called as that varies between observation and that varies between experience. So in this process, can we try to use AI to isolate a particular target of interest from the surrounding? Yes, we can. So this became the motivation in which AI could be used for interpreting certain structures of interest and isolating other structures from non-interest. So in this way, being motivated through these type of concepts, AI started to enter into the theory of reflection seismic, and nowadays in hydrocarbon industry and petroleum industry, the AI is being very efficiently used not only to interpret geological structures from the subsurface, but also to estimate geological properties or rock properties or petrophysical properties. Now, I think I somehow I tried my level best to impress you or to make you motivated to the beautiness of AI and its uses. Now let us see that how this AI has been used through several case studies into worldwide different sedimentary basins, and as well as also Indian sedimentary basins. Now, this is a case study that has been performed that was performed in offshore Canterbury Basin, in offshore New Zealand, and it got published in a very reputable journal of Nature, that is Scientific Reports. What was is so what is the problem here? The problem here is that this is the seabed that you are trying to look at, and below the seabed and at the seabed there are several type of depressions, U-shaped depressions like this. These type of depressions are nothing but what we call as pockmarks. Pockmarks. Now let us try to interpret this. Now this type of depressions that are called as pockmarks. Now, if these pockmarks you are seeing to be present at the surface, that means something is coming from the subsurface or something is rising through the subsurface and trying to hit into the seabed and trying to generate this depression. Now, what are these? Now, if you try to sincerely look into follow the trend below this pockmarks, and if you try to sincerely look below it, then we have very high amplitude reflections present below it, which are nothing but packages of sand deposits or sand reservoirs. Okay. Now, if we further look into below, then we find this upwelling type of structures. Now, can we create, first of all, now can we create a geological problem out of it? Now, what is that geological problem? Geological problem is that if we see certain type of mounded features exactly below this, deep below this, and we are trying to see some type of high amplitude reflections below it, is there any seepage occurring through this and trying to come into the seabed? Now, if this is a geological problem that we are trying to address, then now let us bring AI into the topic. Can AI be used to explicitly showcase this migration process that is going from the subsurface to the surface? Now, being motivated through these questions, we try to understand that how this fluid upwelling is taking place from the subsurface to the surface, and how this type of reservoirs that is present below the seabed is trying to accumulate it and try to and then with geological time it is trying to migrate into the surface. So in this process, we try to through this case study we showcased that how fluid migrations are taking place deep below the seabed and try to come into the and getting streamed into into the seabed, and the signatures of being streamed into the seabed are these type of small depressions that is being observed. Now you see, this is the seabed. Now through the seabed, this fluid is being upwelled. Now, the second case study is on mass transport deposits. Now, mass transport deposits, as a sedimentologist, those people who are dealing with sediments and sediment structures, they are very attracted towards this mass transport deposits. Now, mass transport deposits is what? Now you see this cartoon. Now, if this is the self, and like for example, if we have the seabed, then we have the self, then we have a slope, and slowly, what we enter into a deep water basin. Now, from through this self, through this slope, when the sediments tries to come from the riverine system and they try to enter into an ocean, this type of sediment tries to flow from the self to through the slope. Now, what happens when when the entire seabed is not very much strong enough? This sediment tries to be very chaotic and push each other, and they try to form a rock matrix within it. Now, when they try to form a rock matrix within, the seabed below is not stable, it is unstable. So, understanding this process helps to not only make precursor for drilling boreholes within it, but also it gives a precursory measure to get people updated with some type of tsunamogenic events. So understanding this MTD nature, understanding this MTD process is very, very important for marine geoscientists. Now the question is, from day back when MTD, when people used to interpret MTD, they try to interpret through several cross sections and generating maps at the top and the maps at the bottom, and creating several cross sections through the huge volume of data, and they have to interpret it manually. Now the question is, can ML replace this conventional approach? I must say, you all audience, that this technique for the first time brought a revolution in the interpretation of MTD, where for the first time we generated an attribute called as MTD meta attribute, which got published in a very respected journal of Nature, and this is called as MTD cube meta attribute. And from this, directly we can get, instead of conventionally interpreting what people have been doing long back, we could easily get the three-dimensional structure of these geological features in the subsurface. And this nowadays is being used in industry, and we are happy that our approach will be very, very benefited to some national companies, as well as also we have received many letters from international companies, and they have been also executing this process in interpreting such phenomena. Now, uh, this is a case study 3, where we have some magmatic bodies. Now, again, these type of bodies that I showed you, this type of bodies are in geology we call as magmatic seals. Okay, this type of bounds of concave of nature, where the limbs are translating through the beds. These are called as magmatic seals. Now, in seismic data, they have a very huge difference in density and velocity with respect to the surrounding, and they are and geometrically they appear as such type of feature. Now, if we try to look into the data, then we see that above these limbs, these are called as limbs, above these limbs, certain vent-like structures have been generated. Now, the problem came into picture. What is the problem? Now, as a geologist, you try to model it. First of all, in your brain. Now, if certain seal is there, now if a magmatic seal is there, and and at its limb, I have some vent-like structure, then is it that some fluid is being upwelled, or this magmatic fluid is being upwelled through these vents? Now, now what happened? I try to formulate the problem. The problem is that I have a magmatic seal within it, and above it there are some vents through which the fluids are coming. I am not bothering about the surrounding environment. So being motivated through it, now the question is that, can we showcase in a three-dimensional structure that there will be a magmatic seal, and through the magmatic seal there will be fluids upwelling? Yes, this is the answer to this, where we saw that these type of bouncer features, then how the fluids are being upwelled, how the fluids are getting upwelled, and they are coming to this shallow level strata. This was published in Tectonophysics, and again it is an example from offshore Canterbury Basin, New Zealand. Dear students, researchers, and all at the audience, you try to understand that how this problem is being formed, that how to address this particular problem using AI. Once you generate the problem, once you create the problem, after that, using of AI becomes easier. The only thing what happens during research, or what happens for the PhD students, doctoral students, they are unable to formulate the problem, which makes which makes them delayed, and at the end of the day, what happens? Everything gets complicated. From the day from the right of your problem picking, to the right of your generating the answer, everything should be crystal clear. Like for example, if you look at this problem is pretty simple. What is the problem? The problem is that there will be a magmatic seal. Now above that magmatic seal there is a vent. Now through that vent there are some fluids migrating. So the problem is that I have to image, or I have to interpret, I have to generate a three-dimensional structure of the magmatic seal. And after once the three-dimensional structure of the magmatic seal is generated, I have to showcase that how the fluids are migrating from the limbs. So the problem is now clear. Now, once the problem becomes clear to you, you then use the existing technique, or you try to make some modification to your codes that you have. And at the end of the day, what picture gives you, it will present a very realistic image of your thoughts. So this is the beautiness of how you are addressing, how you are using the concept of geology. You're taking the concept of geology, you're formulating the problem, and once you formulate the problem, you're using some advanced approaches of approaches like, for example, AI, and you're trying to get the solution of it. Now you see here again, this was performed in offshore Norway. Here, offshore Norway, what we have the seabed here, we have the drills, well drill here. Now, what happened? One of these wells have crossed again these type of magmatic seal structures. Now, in normal interpreting these magmatic seal structures, or generating these magmatic seal structures from a single cross section, this is a single cross section, it becomes easy. But there will be several cross sections in strike direction, and when there will be several cross sections in deep direction, identifying a particular three-dimensional structure out of a single cross section becomes tedious. Now, can we use this machine learning approach to get the structure of this magmatic seal? You see how beautifully the structure of this magmatic seal has been captured, and this was selected as the cover page of the bulletin that is published yearly by ONGC, and this was published in the ONGC bulletin of 2020. This was selected among several researchers that have given papers to ONGC. ONGC had selected this as the cover page of their magazine. So in this way, you try to generate this structure. So what happens? The problem is again here simplified. What is the problem? The problem is identifying the structure of the seal. Now, once you get this three-dimensional structure of the seal, you then try to narrate or elaborate that how does the seal geometry of the seal looks like, how the limbs are configured, what is its architecture. Then what happens? When you get certain output, your problem is crystal clear. You got the output. You're narrating the story while you draft your paper and you narrate the story becomes easier. Now, again, this is a case study 5, where again we have shown the fluid migration through hard-linked normal fault system. Now, what are these hard-linked normal fault system? Hard-linked normal fault system means if you have a normal fault, okay, you have a hanging wall and you have a footwall, then you have certain relay zones, some ramp structures within this hanging and footwall. Now, what happens in the subsurface due to several other factors? These ramps, minute faults or fractures tries to develop within these bodies. Now what happens? These minute faults and fractures gets interconnected with each other. Now, in certain situations, if you have a reservoir underneath, and if there is a migration, and if there is a fluid upwelling through upwelling phenomena going on, then these type of minute structures instigate the migration of the fluid from the reservoir towards the surface. Now, in certain cases, when these fault networks within these RAM zones are interconnected with each other, then we say that such type of fault system is called as a hard-linked normal fault system. And if you don't find any type of certain minor fractures or faults within those things, then you don't observe any fluid upwelling. Now you see, this is the geology that we are understanding from the data. Now, once this geology we have understood from the data, we try to see that what is happening within this data, and what type of geological features we are observing. Now we see that within this fault network, there are certain events that are present, and these events might be instigating some fluid upwelling phenomenon. Now, again, when we look to the law petrophysical properties from this law characters, we also we observe that some type of gas seepages has taken place. Now you see, we are correlating both the geological interpretation as well as also the drill well information. Now, after this correlation, what the problem becomes? The problem becomes that what are the faults? Are the faults leaking? So the problem becomes clear that if the faults are leaking, then there will be some fluid migration or the fluid upwelling through these minute interconnected fault zones. Now the problem is that I have to understand, I have to interpret using AI that how the fluids are upwelling through these interconnected fault networks, and what are those and which are those faults which are leaking. So this is the answer to it. So once the problem is clear, now the answer is that we have to the northwestern parts leaky zones, and in the central part there is severe leaky zones, whereas these portions there are non-leaky zones. So we have identified through use of machine learning technique that these are the parts which are the leaky zones, and these are the parts which are the non-leaky zones. Now let us come to Australia. Here there is a basin called as Browse Basin, and there is a reef buried deep below around if I'm correct 1200 meters below the seabed. There is a reef buried. So these reefs are very useful in understanding this geology and geometry of this carbonate reefs are very useful for hydrocarbon industry. Now the question is that instead of mapping this top and bottom, can we bring out this ML to understand the geometry of this buried reef? Now, when we have posed this question, now based on this question, we try to understand the properties. Like for example, the top of this reef is having some capping reflections. We have some high flank deep. We have some low similarity at the edges. Now, if you see the curvature, then we see that the flanks are having positive curvature, whereas the surrounding has a negative curvature. So based on these properties, we try to compute and we try to image only this buried, rather not thinking of the environment. So what happens? So the environment that I'm not thinking of, I'm making it as a feature none, and the environment that I'm thinking of, I'm making it as a feature yes. So now the problem is clear. So now once the problem becomes clear, now I try to use ML technique and I try to understand the structure of this buried reef. This paper is in review and in geoscience status. Now let us come to India. Enough is now on worldwide sedimentary basin. Now let us see what is our motherland India saying to us and what is happening in India. Ganga foreland basin is a very petrol is a very basin is a very prominent basin in which the national oil companies are nowadays focusing for its exploration. Now, what was the challenge with us? It was present that that there are certain events within these data or within these areas where we had certain type of like bounce features, and we had certain fluid upwelling phenomenon going on. Now, initially, when we look at the data, but here we could not understand that what now there are several results published by NGRI. They are saying that in the surface they are having some gas seepages, but but close towards the surface we did not encounter. We are not able to understand that what is happening in the near surface strata. So what we did is that the question is that to understand or to make the observations of the geochemical anomaly, or to make it agreeable with the geochemical anomaly, can we build up a story showcasing that the fluids have migrated and exactly hit at those geochemical superficial positions. So that was the problem with us. So now, based on this problem, and when we tried to extract certain attributes, we found that some minute fractures might have been occurring within this near surface strata. So based on this geological information, we try to enter into this ML and we try to enter the model. So this model clearly shows that through this mounded structure, yes, there are certain hydrocarbon seepage going on, rather in a very focused way. You can see it is a very focused way, rather not going here and there. It is traveling in a very focused way towards the surface. And in the near strata, there are there might be some minute fractures that are allowing these type of fluids to come into the surface. And in the surface, when it comes, we are getting some geochemical signatures out of it. So in this way, we have tried to showcase this fluid upwelling phenomena in the Ganga basin, and we have submitted this article to Journal of Applied Geophysics. Now let us come back to Upper Assam Basin. If you see towards the Upper Assam Basin, the challenge with us was to use convolutional neural network UNet and to map these fault networks. Here we have in the Upper Assam Basin there is a very the known reservoir of the Upper Assam Basin are the sandstone units, and here are this is the top of this formation, what is known as the Tipam formation, and this Tipam formation has been compartmentalized through several geological faults and that have compartmentalized this Tipam. The challenge was that can we use convolutional neural network and map this type of features, and we have used this convolutional neural network to understand that how the fault networks have taken place, and this green arrows clearly shows the presence of these faults in the cross section, and this is the 3D view of it. This is also same type of work that we conducted in the Upper Assam Basin, but the 3D survey area is a different, which what is called as Chandmari, and we try to use the unit architecture to map these fault structures. Now, apart from this mapping of the structure, there are also certain lithological properties or petrophysical properties that also needed to be understood. We have used an algorithm of random forest where we use a random forest algorithm to accurately construct some missing log, as well as also some of the logs which were not accurately captured while logging the subsurface. And we have achieved a good correlation of 0.8 to 0.9 between the actual and the predicted log. So the final conclusions of my today's talk is pretty clear, straightforward. That is, artificial intelligence automates the process of subsurface interpretation by limiting human intervention. Artificial intelligence mimics human brain and produces realistic outputs at much reach. Artificial intelligence improves subsurface images that provides greater insights for the detailed understanding of the subsurface resources. Here is a handy kit for all young students, academicians, and researchers out there. I must say that this is a book which has been recently published by the prestigious American Geophysical Union and John Wiley and Sons. I'm fortunate and I'm thankful to Dr. Kalachan Sen. I participated with him, and I have been one of the co-author of this book. You can Google it, and I think NIT your library can purchase some of the copies of these books, because it is, I think now, I think if I have heard correctly, ISM Dhanbad, IIT Kanpur, they have already purchased these books, and people who are interested in working seismic data interpretation, they have they find this book as a handy toolkit for their use. Here are some of our collaborators that we have been working with: ONGC, Director General of Hydrocarbons, New Zealand Petroleum Minerals, Cardiff University, IIT Kanpur, University of Western Australia, DGB Art Sciences, and Harvard. Thank you all for your kind attention, and thank you.
Thank you, sir. Thank you for wonderful session.
Thank you.
All the participants, we will share attendance link in chat box. Please stay. Any participants have any doubt? Yes, participants. Thank you, sir. Thank you, Chinmoy sir.
Yeah,
Thank you very
thank
much.
you. Thank you. Thank you. Thank you.